morning, everybody. This is day 2 of chapter 23, which is doing means instead of doing proportions. So we're going to be continuing with what we did yesterday. Yesterday we did confidence intervals for means. Today we're going to go over the assumptions and conditions, and we're going to do a problem. So confidence intervals for means. Student T models are unimodal, they're symmetric, and they're bell-shaped just like normal models. But the T model, with only a few degrees of freedom, meaning not infinite like we talked about yesterday, has a much fatter tail than normal models. And that's what makes the margin of error bigger. So here's an example of what they're saying a T model with 2 degrees of freedom. It's extreme, the difference between them. They look similar, but you can see down here at the bottom that they're much fatter. They get fat, so they kind of go out for much longer than, getting closer and closer to, 0 probability. So it looks the same. And as I mentioned yesterday, as the T model, the degrees of freedom get closer and closer to infinity, they will become normal. So let's go to assumptions and conditions. So we talked about Gossett yesterday, the guy from Guinness who created the T model, and Sir Ronald Fisher. He was a economist who received the Nobel Prize. He actually mathematically confirmed and gave us the true way that we do it in statistics with the T model. So there's a few similar assumptions, and then there's one or two, just one that's different. I will have a sheet for you. It's not a cheat sheet in the sense of like anything cheating. It's going to be your notes. We will talk eventually in a few weeks about how we're going to set up our table when we're getting ready to take this exam. I don't want you Googling things. It's going to take too long. I don't want you paging through the book. It's going to take too long. We're going to have our notes kind of spread out around us. So if we need to, hopefully we won't, need to refer to them, we can do that. So the assumptions and conditions for using the T model, which is going to be for means, is going to be the independence assumption, which means that the data values are independent, fine. Random, we would like it to be a simple random sample. Representative is fine as long as we can make sure that the representative sample is truly representative. An example I was thinking of today is if they wanted to know the percentage of students in HenHUD that take the AP, they wouldn't just ask freshmen. That wouldn't be representative. They may predominantly ask juniors and seniors, though there are a few sophomores that take the AP too. For world, for instance, but for the most part, it's mainly juniors and seniors. So you wouldn't really ask an underclassman any of those things. That would not be representative. 10% condition, no more than 10% of the population. So those 3 things are the same as we've been seeing for proportions. So we have to remember that now, instead of having a success failure condition, obviously we can't have that. We don't have the proportions to do that with. We're going to have a normal population assumption. So for means, we're going to have a normal population assumption. We can never be certain that the data is from a normal model, but we're going to check it. So what we're going to do is we're going to create a histogram. Sometimes they give us the data and the histogram is already there. That makes it very easy for us to say, oh, it's unimodal and symmetric. Oh, it's unimodal but skewed slightly to the right. Or, oh, it's heavily skewed, and that's what we're going to talk about. So this whole time we've been doing this class, we've been talking about this number, what's appropriate for the sample. And certainly when we're doing proportions, the NP, NQ has to be greater than 10. Fine. That's going to allow us to see that it's large enough. When we're dealing with means, however, when we're dealing with the T model, which is what's going to be used for means, we are going to have pretty much these 3 parameters. And it's kind of a little loosey-goosey. We get to the number 15 and the number 30, 40, they're saying in the book. So let's talk about this here. Smaller sample sizes, less than 15. the data has to follow the normal model, unimodal, symmetric. Okay, has to follow it. If it is not unimodal and symmetric, we have a problem. Now, that being said, if we only have 3 things in the data, which would be extremely small, but could happen, it's going to be hard for it to be unimodal and symmetric. It's really in real life, it'll be very hard. So really, hopefully most of our examples will be around 9, 10, 15 or so. Moderate samples, so between 15 and 40, they're saying. I also have seen 30. Hopefully the examples will either be smack dab in the middle, like the number 25 or something, or they'll be really big, like over 100. That's what I would hope for. But between 15 and 40, they're saying it has to be unimodal and reasonably symmetric. So no major skewing. So, slightly skewing is what I would say. Large samples, we don't care if it's unimodal, but it can't be extremely skewed. What would be an example of extremely skewed? I don't know, all the workers at a grocery store, and then you have the CEO of the grocery store. So you have all the workers making $15 an hour, and you have the grocery store CEO making millions. That would be extreme skewing. Otherwise, hopefully we won't see that too much when we're dealing with large sample sizes. What's a large sample size? There's the book saying over 40. I've also seen it over 30. Just back up your work. So what if the number's 32? I hope the data would be unimodal and only slightly skewed. Okay. So let's look at this example. This is from the book, but I want to talk about it a little bit. Before we go on, they have this nice little box in the book, and I wanted to just focus on it for a minute. When we're doing assumptions and conditions, we haven't really experienced this too much. Maybe once or twice we experienced where we're like, I don't feel comfortable saying it's truly random or something like that. The disqualifiers we won't immediately stop. So if by chance on the AP or on one of my tests, you for whatever reason have come up with the fact that the assumptions and conditions have not been met, you will state that and you will say you're going to proceed with caution. So what are they saying in this box here? They're saying that if it's not a simple random sample, if it doesn't say it's random, you have to say that it's representative. But if you don't feel comfortable saying it's representative, or you can tell the data is not representative, you need to kind of mention that. Again, proceeding with caution. They're also mentioning things about outliers. You're supposed to perform it with and without. Sometimes we don't have that option. We could see the histogram, but we can't see the data. That's always a concern. And then I think that's all I wanted to say about that. So I thought that was a good little box kind of saying, hey, you're not going to stop, but you're going to just say, I'm proceeding with caution. This is a concern of mine. Boom. Okay. Voluntary bias is a good example. We're going to keep going with whatever they give us, just proceeding with caution. I would hope that the AP is going to be extremely, extremely good in the writing. They usually have a year to write these things. They've had to now revamp it over a few weeks. And my opinion is the more they have to revamp, the more room for error. So when I make a quiz, the night before a test is supposed to happen, sometimes I make some errors because I haven't had a chance to look it over, to think about it, think about whether I've taught everything to you, etc. It just, the more time I have to look something over, the more solid I think my questions are. So it's just something to think about. So let's see here. We're still talking about the salmon farm like we did for yesterday. So those who didn't watch yesterday's, watch it, please. And then they want to know, are the assumptions and conditions for inference satisfied? So again, we're talking here about these decimals are not percentages. They are the parts per million of this carcinogen Murex that's in the salmon. So let's talk about this here. The salmon, they're talking about 51 farms, 8 regions, 6 countries. They're going to be independent of each other. The independent fish, dependent fish, 2, random. This is random. They're picking 150 salmon from 51 farms, 8 regions, 6 countries. I don't know if they originally said it. Let me just look in the book real quick if they even said that it was random at any point. However, I feel that's not that. Where's my salmon question? Here it is. Let me look here. No, it doesn't ever say that I can see in the original book that it's random. It's random. They're asking for 150 different fish across 6 countries. It's random. So I can say this is random. I don't even need to kind of clarify. That's random. 3, is 150 fish less than 10% of the population? Absolutely. 150 is less than 10% of salmon population. Salmon. That's an N, population. Final question 4. This is going to be the one that's new. The normal model condition. Has the normal model been met? So let's talk about this here for a minute. Let's look at the picture. The picture is certainly showing us that it's unimodal for certain, and it's 150 fish. So it's above the threshold of being mildly large. It's large. So we can actually say that because this is assumption number 4, 150 is large, we can use normal condition. Okay. The normal condition has been met because it is a large sample size. By the way, the graph is not skewed. I mean, there's some slight skewing. It's a little more to the right than to the left, but it is definitely unimodal, mildly skewed, but it's not a concern with 150. Okay. So all the conditions have been met and we can proceed. So let's do a problem together. This was what the original book started with, so I kind of grabbed 2 pieces of data. Take a moment to read about it, and then we're going to go through. I would like for you guys to follow along with your calculators because we haven't really done any of these, if I believe, in the percentages side because we weren't doing means. So this is going to be the first time I'm going to be using the stat edit function to do inference. So let's take a moment, and I'm also going to scroll down so you can see the data. Okay. So what this question is going to ask ultimately, let me go down to the bottom so you can see it, and then I'll scooch back up. You can pause at any time. We want to build a 90% confidence interval for the mean speed of all vehicles traveling on Trip Hammer Road. The interval that we'll make is called a 1 sample t interval. So when they ask for panic, when they ask for name the interval, it's going to be 1 sample t interval. Okay, and then it's saying what can we say about the mean speeds of all cars on Trip Hammer Road. So let's do this. Okay, I'm going to do it longhand, and I'm going to do it using the calculator as well. So I just want to do both. I want to put down some information for the readers as well. So the first question is the panic. We're dealing with car speeds. On whatever this road is, Trip Hammer Road, I'm going to call it, okay? TH Road, okay? So the assumptions and conditions, let's go through them here. I didn't have a chance to fully read this in the last few minutes, so let's take a look. So basically, they're concerned that just having a posted speed limit number, and sometimes having the police there isn't really helping the speeds. They want to know if people are, they want to know if people are speeding. We'll talk about that soon too, tomorrow when we do tests. But resident stood where he could see a detector and recorded the speeds of vehicles passing it during a 15-minute period one day. When cluster of vehicles went by, he noted only the speed of the front vehicle. So the assumptions and conditions, the independence is being met because he's only focusing on the first vehicle that goes by. If they're driving in a cluster, they're not going to worry about it. So that one certainly has been met. Random. He's doing a convenience sample. He's standing there for 15 minutes at one part of the day, and we've talked about this a lot. If he's standing there at 7:30 in the morning in front of a high school, the cars are going really slow because they are all turning into the high school. If he's standing there at, I don't know, 12 o'clock in the afternoon, cars are probably going faster. If he's standing there at 8 o'clock at night, the cars might even be going faster or maybe slower because they can't see as well because it's dark. In any case, 15-minute period, I'd be a little skeptical about it. So I might actually mention that. So let me talk about this. So independent cars of each other. Dependent cars of each other. random, more convenient than random, a bit cautious about this condition. Is 23 cars less than 10% of the population? Absolutely. 23 cars is less than 10% of all cars, most likely on that road. If they're complaining about speed, it probably is. So the final question is about the nearly normal condition. So the nearly normal condition, let's go back up. So we're dealing only with 23 cars. So it's kind of in that middle range. It's not going to be small, under 15, but it's not going to be above 30 or 40. We're 23. So how would I discuss this graph, this histogram? I would say that it is unimodal. I know there are 3 bars together. That's considered unimodal when they're all together like that. And it is slightly skewed to the left. By the way, I put this data into my calculator. I'm just curious. Give me 1 second. I didn't look at it yet. I'm curious if I turn on my calculator to do the graph of the histogram. I'm curious to see L1, zoom 9. So that's how it defaults when you put in the data. If they only gave me the data, all the speeds, and not the histogram, that's how it looks. How would I describe it? I'd also say that it's unimodal and it is roughly symmetric, or it's mildly skewed. What I would say is on this is that your goal, if you can, is to make the graph work for you. You want to proceed at this point in our statistics career. We're not statisticians yet. We're in a 101 course. We want it to succeed. We want to be able to do the test if all possible. So this is something you're gonna want to tweak the window if you needed to. And I'm just curious if I just change it. The smallest number was 21. The biggest number was 38, I think. They're saying 40. I don't remember seeing a 40. 38, I think, was the biggest. I'm going to change it to 39, and I'm going to do it in increments of 2, or how about 3? And then I'm going to do graph. Kind of looks the same. Okay, as what I had seen before. So we would want to tweak it a little bit. It looks like he's going in the book in increments of 2.5. Yeah. Looks like he's going in 2.5. In any case, I would definitely say that it is nearly normal because it is unimodal and mildly skewed, or I'd say roughly symmetric. Okay, so therefore, all those things being met, all the assumptions being met, the N, since all assumptions were met, can use 1 sample t interval. Now, what am I going to write down from the data? So before I do the interval, I do want to write down a few things. So again, go to your calculator, put the data into stat edit. This is good review too, because we haven't done this in a long time. Stat edit, put your data in there. Okay, you can pause this video, put the data in. There's 23 pieces of data. And then to see the mean of the data and the standard deviation of the data, I'm going to go to stat, calc 1 var stat. I'm doing list 1 and I'm going to calculate, and I can see that my X bar is 31. So my X bar, this is what I would write. I would write this stuff down. I'd write X bar equals it's just 31. That's 31 miles an hour. And the standard deviation, that's the S, it's not the population because we're only doing 23 cars over a given time period. Where's my thing? Is 4.25. Now, I don't need to do this manually. I can use the calculator for this. So when you're using the calculator, when you go to, so they want to do a interval. This question is saying, what can we say about the mean speeds of all cars on Trip Hammer Road? That's when we're going to say something about we are 90% confident that they'll be between these 2 speeds. And again, this is a number, a speed, not a proportion. We're going to go to test. We're going to go to a t interval. Number 8. I'm going to go to data this time. L1, frequency, I don't know, frequency 1. Yeah, I guess we keep that. And then I'm going to put in 90. Remember, if I was doing this longhand, I would have to do, from my sheet, I would do the 2 sample for 90, or I would go to my 1 sample for 95, right? And I'm getting 29.5 to 32.5, I'll say, okay? So my interval, my I, is going to be 29.5 to 32.5. So what am I going to say? I'm going to write it. We are 90% confident that the true mean speed of all cars on Trip Hammer Road are between 29.5 and 32.5 miles per hour. If you recall, the speed limit was 30 miles per hour. So the question is, what can we say about the mean speeds of all cars on Trip Hammer Road? We're 90% confident that they're going within the suggested speed limit. Okay. The cars are going within the suggested speed limit of 30 miles per hour, because it's in between that interval. So this person is upset for no reason. Last thing I just want to mention is that you have what would a 90% confidence level mean? It would mean that if we did this sample over and over again, 90% of our samples would contain the true mean. Okay, we're going to have homework today, page 555, number 13 and 14. I would like for you to do those and submit them to me. They'll be due, I'll make them due on, what's today? Today's Wednesday, Friday. Have a great day, everybody. Bye now.